a phase where instead of being a hammer going around looking for nails, we're essentially looking at the nails and evaluating, hey, would hi-hat or would something else be a particularly good hammer for that, and looking at how it is we may want to apply or extend hi-hat to see whether it's the most relevant solution. So one of the things that we've seen is that there are a number of cases where you may have different device types and you may want to share memory among those, and want to look at how it is that we can have a general enough mechanism for being able to handle what could come our way. So that's kind of the been worked out in the context of. So I will give a little bit of context, define some terms, and illustrate things, show how these different pieces and parts work, and like essentially for you all to look at this with an eye to, hey, what do you want to do with managing memory, and is there anything that we are not actually supporting adequately relative to what it is that we might want to do with this. So hopefully that all makes sense, and we'll jump in. So the first thing for context, I'll just, I'm intending for this to be very general, but I'll give a common example of where you may have a couple of CPUs, each of which could have a couple accelerators hanging off of them. And I've named each sort of set of these as an A and B set. So you then may have some distinction between who it is that's running the code that manages the allocation of memory, and where it is that the resources that are being allocated live. So that's a distinction between an agent and a target. So it's commonly the case that a CPU, for example, might be used as an agent for managing memory on some attached device. The device may not itself be smart enough or fast enough to manage its own memory, and to the extent to which that's the case, somebody else is managing on its behalf. So there's not necessarily a one-to-one correspondence between the allocation agent and the target. So we want the flexibility to be able to specify and control that. It's also the case that you may decide something like, well, there's, for the sake of locality or something that's going on with partitions or whatever, we may subdivide the overall resources and say, hey, CPU 0A, you're responsible for managing a particular subset of the resources that are hanging off of you or that are accessible from you. Even if those aren't uniquely accessible to you, the things could be partitioned in that manner. So this is sort of the general case for here. And I haven't shown memory resources and so on hanging off of these, but I'll get to that. So any questions here before we go ahead? All right, straightforward enough. So allocation agent is the execution resource where the code does the allocating. It's named since it may not be the local source thread. So I could say, hey, the agent is some other thread, maybe on the same CPU, but a different core or a different CPU thread or different package or whatever. And it also could be a specific resource or any one of a set of resources. I could say, I want to do my allocating. I kind of want it to have this locality, but I don't really care where it runs. I could just set the thread affinity for the thread that gets woken up to do that if it gets woken up, or maybe it's pinned and just waiting for work or whatever. But it could be any one of several different guys. And so if you want that flexibility, you have that. So I'm also going to try to be clear here, trying to come up with an architecture that's flexible, but we want to make it so that you don't have to pay too much of a price in performance overhead for that flexibility. And we'll talk a little bit about how that's intended to work. So the allocation target is a set of memory resources to be allocated from. It supports a set of possible target resources. And an example is I could have managed memory that allows migration between some subset of the compute and resources and memory resources, like a CPU and a couple of its accelerators. And I could arbitrarily restrict where and when and how it could migrate. So we haven't gotten to the policies yet, but here we're just talking about the targets. And resources could also be all of a physical resource. I could say it's any one of or all of the threads on this particular CPU, or it could be a specific subset. Or when I refer to memory, I might refer to all of the memory on a resource or just a particular subset of that. And we haven't actually implemented and started exercising this part of it yet, but I'm thinking that bit sets could be good for just like Linux uses for CPU sets. In some cases, if you deal with memory and sort of portions of memory, bit sets might not be the right answer for dealing with large partitions of memory, but we can innovate together and figure out the right thing to do there. So any comments on this before we go ahead? Either you're all sleeping or you're all agreeing. Hope you're not sleeping. Okay. And go on. Next thing is selection. So memory may have several different things. It could have different kinds. It could have different locations. It could have different depths. And the notion here is that each specific instance has its own unique resource handle. So I could have several different banks of memory, or I could have high bandwidth memory and some non-volatile memory. Those are different kinds. I could have them hanging off of different CPUs. I could have them not associated with CPUs and just hanging off of the fabric. There are a variety of different, the combinatorial possibilities here. There could also be several kinds of allocators. So this is the software that runs, that does the allocating for the same resource. I could decide that I want to have one allocator that essentially shares all of the memory resources, sort of for all threads and all devices, or I could have it be per thread or per device. I could have it, be unique per memory resource or per execution resource, or I could have something like a same size allocator. And so you have the ability. I didn't think to draw a picture for this, but you could essentially have something wherein you could say, I can either statically partition and say this allocator gets this fraction, and that's statically determined of the memory resource, for example, or I could say you get a guarantee, this allocator gets a guaranteed minimal fraction. Suppose there are 4 quarters, it's guaranteed 1 quarter. Somebody else is guaranteed another quarter, and then they can fight over the other 2 quarters, and it's sort of on a first come first serve basis. So as far as Hi-Hat's concerned, it totally doesn't care what it is or how those things interoperate or whatever. It just has the flexibility to be able to describe and specify and select based on whatever has been provided by an implementer. So none of these, an allocator itself is not part of the Hi-Hat dispatch APIs whatsoever. But you can have an allocator implementation that's conformant with the Hi-Hat architecture that can be used to plug in. And the selection, comment there? Okay. Feel free to jump in anytime. The selection is based on either on the combination of the compute and memory resource, and I'll show you how that works, and also potentially a chooser. So if I have several different allocators, I can just say, use the first one, whatever it is, or I could say, use allocator number 99, which I know about because I caused it to be registered and I want that one. And I don't even have to say the third one. I can just say, 99 if that's what I decide. And so there's a fair bit of flexibility that we can work out as to how it is we do that. And all actions essentially have an execution policy parameter as part of the action API. And so that chooser is part of that data structure that's part of the execution policy. And that's what you'd use to select it.
Can I ask a sort of process question, CJ?
Sure.
So there's sort of multiple stages of where you want to make these kinds of decisions, right? So when you're writing the code, you want to make a fairly loose association. I need the following kinds of resource while I'm developing the algorithm, and then there's a sort of binding phase where I say, okay, I now know what kind of resource I'm running on, and I would like to, associate these, these blocks of memory with these resources, et cetera, and there may even be a lockdown where you say, okay, I ran it, it worked, I want it to be consistent, so whatever I learned from the last run, I want to make that fixed. I think the way we've talked about hi-hat before, hi-hat is only the latter stages of those. It's not really the language in which you sort of do the high-level description. Is that correct? Are you sort of seeing this as the binding between the application or between the algorithm and the hardware, and that it's more direct? Or are you seeing this as a potential annotation during development of code?
I'll try to answer that using different words, and then you can tell me if I've answered your question. It's a non-goal of hi-hat to provide a user interface to be able to specify or control this. So we expect to be something that makes the implementation, optimization, and testing as infrastructure beneath somebody else's interface easier and more effective. Second point is that the managing of exactly, all the policies and making scheduling and binding decisions, as you alluded to, I think of scheduling as being binding and ordering. That's all done above the hi-hat layer by some other hi-hat client. And they're the ones who say, here is where I know where I want the allocation to happen. I know which execution resources I want to be used to manage the allocation. I know what the policies are for whether it's allowed to migrate or whether it should be reduplicated or whatever. I know all those things. And I'm just using hi-hat as a dumb pass-through through an architectural interface down to somebody else's implementations, which will implement those things. So hi-hat is just dumb. It just passes the information through and gives you an architectural interface by which somebody who is a hi-hat client can specify what's to be done and can know whether the implementation has been registered from beneath to make it so, and then can have the confidence that it'll happen.
Gotcha. No, that did answer it. Thanks. Yeah, that helped a lot. And you've said this before, and I'm sort of just making sure that I'm still on the right page, which is that there could even be a runtime up here that's making runtime decisions, and it's effectively outputting hi-hat. So some of this may be code developed on the fly. So if you wanted to deal with resiliency, you wanted to deal with dynamic allocation, that's all above the hi-hat layer.
Correct.
Cool, got it. Thank you. I just wanted clarification, and you did it. Thank you.
Yep. Okay. Any other questions, comments?
I had one quick question, actually. You mentioned you could have different contexts which point to maybe different portions of a CPU or different accelerators. Would this design allow for different contexts to overlap resources? So say to have two
Yes.
contexts pointing to the same threads.
I think it's important to be able to do that, yes.
Yeah. Okay. Okay, thanks.
And that is very much a policy decision of something above as to whether it wants to guarantee mutually exclusive access or partially overlapping access, and decided who wins under what circumstance and all that stuff. So we want to allow full flexibility for being able to do that, but and that's part of the intention of this execution policy field, is that if there's need for communicating various other policies that are usage specific as to how all that should work, then that can be included.
Yeah, I agree. It's good to have the flexibility at this level, but then a runtime system above can decide how that's managed and distributed.
Yep.
Great, thanks.
Sure. Okay. So moving right along. So let's talk briefly about resource enumeration. So when you want to ask the question, what's there, you probably want to enumerate it once. You know, if you want to say, well, tell me about all the memory resources. You don't want to, if that memory resources is reachable via multiple routes, you probably don't want to enumerate it each time. You might want to enumerate what the connectivity is, but when you just ask, you know, tell me about the resources that are there, you probably want to enumerate it once to avoid double coverage. You also probably want to enumerate how it's connected, the number of kinds and characteristics of links. And then there's the whole notion of cost models for access characteristics, for unloaded and shared loose, and bazillions of different combinations of different kinds of things. So I think that we can agree on, as a community, on sort of a core set of basic enumerations of what's there. I think we'll want to have an extended target specific enumeration of additional features such as connectivity and costs and order and those kinds of things. And that enumeration can inform the cost model, but I expect the cost models to be very specialized for each scheduler. And so that sort of gives you this stack that's over at the right of where we're starting with the core. We have an architecture that's extensible. You can plug in the implementations beneath. You can build your own abstractions on that can include things that the scheduler and its cost models will use, and then you can offer whatever abstractions you want to on top of that again. So we want to, from a hi-hat perspective, you want to know who you are, know what you're good at, know what you can agree on, and sort of keep it simple and streamlined. So now I'll go into a bit of detail on that. So we want to be able to enumerate compute resources, memory resources, and we model those as hanging off of compute resources, even if it's a null resource. And we want to enumerate it once, even if it's associated with multiple compute resources. You have some way of doing that, and that's talk to the HWLock guys, and they were cool with that. So, and this is exactly how it is that you do this enumeration is actually provided by an implementation. So we give an architecture which enables the enumeration as part of the hi-hat APIs, but then you plug in an implementation, so you can build an implementation on top of HWLock if you want, and then use that. And then this notion of enumerating the connectivity between the compute and memory resources, we don't have a complete design and implementation of that yet, and since we don't think the communities all can agree on one thing, we're going to want to have some sort of a flexible and extensible interface. Maybe we'll have some prioritization of equivalence classes, and you can guide the selection via priority, whether it's connected or not can be part of that. Or you could have costs that depends on direction, or read-write mix, or granularity, or queue depth, or all kinds of a billion and one things. It's way too complicated. There's way too much richness, and nobody's going to care about. Most people aren't going to care about that detail, and no matter how much detail you provide, somebody would be unhappy. So I think you have no choice but to do something that's pretty generic and then make it extensible from there. So I'll just make a couple more comments and then open this up here. So you can think of having different kinds of devices and then specific instances of those device kinds, and having different memory kinds and then specific handles that are associated with given instances that are hanging off of those devices. And this shows a nice clean fan out, but that doesn't, what happened? I think I have a hidden slide. I do. Let me unhide it. You could have other ones that are shared that look more like this. And so this is an example of where this purple dude, you probably only want to enumerate him once, but you may show up him as being connected to multiple other devices. Okay, so again, this is sort of the approach that we were looking to take from this, and I can just record, is anybody particularly interested in participating or, passionate about how it is that this connectivity and the cost models and stuff would be enumerated and managed, and that wants to join in discussions about that? We're sort of kicking that can down the road until somebody cares enough.
I think this is something we'd be quite interested in discussing if there were to be a separate discussion on this.
Okay, and that's Gordon?
Yeah.
Okay, anybody else? Okay. Just taking a note here. All right. Is this clear enough to everyone as to how this is working? Any questions on this? Okay. So on to the more fun part. How does this actually happen? So first, a review of registration in principle. So remember that Hi-Hat is basically a dispatch framework. So it provides an architecture of what the functionality is that should be provided. And then it's up to somebody who's administering the system or the user to make sure that implementations of all that functionality actually gets registered. So you say, here's my implementation that will work on this particular set of resources and this policies. I'll tell you what I support as I register it. And so if you ask for something that's of this functionality, so you can register with a particular Hi-Hat API code and say, these are the resources that I work on, and these are the policies that I support. And so then it'll go and try to invoke something that, and ask, hey, give me the thing that's registered to do that. And then if it finds it, great. If not, it'll give an error. Or maybe in a non-debug mode, it'll just presume that it's there, and bad things will happen if checking that turns out to be too much of overhead, or you're going to have a debug mode or non-debug mode. We can sort out what makes sense there. So the registration and the allocator querying essentially use the same mapping, and that's based on the compute resource agents and the memory resource targets and the policy or selector. And so when you register that, it says, oh, this can run on a set of compute resources and a set of memory resource targets, and I'll give an ID to that, so that when you register the set and create the set will have an ID, and the system will know what that ID is, and when you refer to the set, then it'll have an ID, and then you can use that ID to look up in a 2D array. So it'll say, based on this ID, the compute agent ID and the memory target ID, it's a simple direct lookup. So you may get some cache misses for that, but if it's cached, that's even better. You will be sort of making an indirect memory reference. But the notion here is, don't make it so that you have to make evaluations about subsets and other kinds of things every time you want to call one of these things. So that puts a little bit of a burden in that you need to put together the set and say, this is the set, and come up with an ID for that. And if you want to do weird things to say, I want this thing will work for the whole set, for relevant subsets, for each individual resource, you can take the same thing and you can register it multiple ways so that the speed critical lookup is still fast and direct. And maybe that's a little bit more complexity for when you go to come up with how to reference it, but you still maintains the speed. So we kind of went for speed in this. And I'm way too worried that if you do something dumb and codify some complicated lookup that starts to look at arbitrarily complex subsets of things, that you're going to be totally hosed from performance. So any feedback on this approach? Is it clear what's going on here? I need to explain more. Okay, hopefully it's clear. All right, so now we also have to deal with other more general cases of dealing with memory. So among the things are migration and mirroring. So a memory object could be read and written from multiple execution resources. It could reside on any of multiple memory resources. There could be many local things, there could be many remote locations. So there are a variety of different policies that you could have. You could replicate read-only copies. You could do that from the start, because I'm pretty sure I know I'm going to need them, or you could say only do it as needed. When it comes to migrating writable or read-only instances, you could basically suppress migration, because I have a preference. I occasionally am going to use this remotely, but almost all the time it's going to be staying in this one place. So don't be thrashing them around. Keep them where I told you to put them. Or you could move it around. And where you put it could be based on proximity. It could be prioritized based on need for capacity, whether you're using high bandwidth memory or nearby bulk DRAM or system memory or network attack storage. You could prioritize based on specialized access, whatever. And again, Hi-Hat doesn't care. You want the full flexibility for a variety of different options. And so you can then sort of specify what you want for this. So the idea that we have is our notion of a data object is a data view. That's your view that you have for this thing. And so you can record these policies as metadata in the data view and say allocate it with these policies. And I can specify some initial conditions. Some of those properties and policies can be mutable if I want to change them over time. And some examples of this are mmap, or in the CUDA space, there's the notion of CUDA mem advise, which has quite a bit of flexibility for specifying what your initial affinities should be and where and when you should create mappings for things and so on, where you want to register, that sort of thing. And that metadata can include the set of memory resource targets, where can I live? What's my initial affinity? Where am I going to be pre-registered? Registration can cost you something, so you don't want to just do it everywhere. You may want to specify where you want it. You may want to move that registration cost to allocation time versus having it be reactive, and all the different migration policies and access limitations we talked about. Just to note, for some scenarios and targets, two different agents could both have access to something, but it may be mutually exclusive access, where one gets to write it, and then there's an assumption that the other guy won't read it while he's got it, or won't write it, and so you need to manage that. And so that's another thing, again, that can be pushed up there. And then you can communicate this to the underlying runtime at the time that you make an allocation request, and that information can be bundled from the allocation API interface using the execution policy field. So this is essentially the what's being implemented. So to make this more concrete, this is the regalloc API that's being proposed. And so here's the allocator, is the pointer to the allocator that I'm going to use that's meaningful on a particular set of execution resources. And it's being used for a particular set of memory resources. I may have some target-specific configuration that I'm using for this. And I may choose sort of which of several different registered implementations this is for. And then I may also have a bit vector of supported traits saying, I know how to pin it, or I don't know how to pin it, or I know how to initialize it to 0 or not. So that if somebody asks, hey, could you pin this for me? You can programmatically ask among the different implementations that have been registered, do I have the ability for it to do it so that I don't have to explicitly execute code to, and sort of which ones are available for me to use. And once the scheduler knows that, the code that's either in the Hi-Hat client or the user code above can go and query, hey, tell me what support you actually have, and then I'll stick within the bounds of that, the confines of what's supported. And if I try to ask for something that's not supported, again, I can do some some basic error checking for that. And this is, again, how you'd register that. And then I may want to turn around and query what it is that's been registered. And I can basically say, tell me how many things are registered for this particular set of execution and memory resources. And then, give me the pointer back for the nth one. Or I can essentially say, here's the chooser value that I have, give me the one that matches this chooser value. So they're sort of two different flavors of this. I only showed one here. So any questions on these APIs or how that works? All right. And this is basically, we just talked about registering and querying what's been registered. And then when I go to do the allocation, I'm saying, please allocate me some memory. And as a user or as a client, I want to get back this data view that gives me a handle to this data view. You pick the address. I didn't, in this form, I'm not registering an address, but you picked it. So tell me what the address is. I told you how big it was. I told you what set of traits I wanted it to have. I told you what the policies were, which could include the chooser. I want to tell you some other execution config information and what resources to do the allocation on, what the targets are, what the input dependencies are. Don't do this allocation until something else has been satisfied, and then it'll pass back an action handle, which I can use to query whether it's done and use in the rest of the dependent system. So sort of the end-to-end usage of this. So again, this enumeration of connectivity I talked about before isn't yet supported, but the kind of thing that we're thinking of is, hey, given this execution resources and these sets of memory resources, give me this, I don't know, user-defined something object that describes the connectivity costs. And that can be a void star, and whoever registers it can know what form it's going to be in and then can interpret what comes back. And maybe we can come up with a smarter answer for this, or maybe Gordon will solve all these problems for us. So we can look at what makes the most sense there. That's sort of speculative. So just some things that we're pondering are, do we want to support a copy on write? We could add that support as a trait. Do you want to, is the support going to be limited to the least common denominator multiple targets? It could be, but you could also use different allocators for different subsets of resources, giving you more generality. When you want to ask questions about how exclusive access is managed, whose turn is it to have this? I think there are really two choices here. We decided that the implementation of the Hi-Hat dispatch code, it's supposed to be dumb. So it's not supposed to track, hey, who's got the latest instance, or which ones are valid, or which ones are close by. That's really left up to what's layered, to other layers. And those layers can actually be above or below. It could be managed totally in the implementation that's plugged in from below, and you could push all the smarts down there, or this is architecture. The implementation for this is mostly done for the stuff that's here. So any other feedback of, we're interested in understanding your usage models as to what you need and validating them against that. Also want to know, what else do you want that's not listed here and not supported? If George, I'm sure, is waiting with bated breath, and Damien to ask about multi-dimensional stuff. Or if you think that this looks appropriate, or you think something's glaringly missing, or you're worried about performance or whatever, now's a good time to speak up. Silence. So any comments on? Can anybody come up with, for different usages that you have in mind? Does this seem like it covers stuff that you would have in mind? Want to use it? Like the guys at PNNL, maybe I'll pick on you first.
This is John Fay. Am I the only one from PNNL that's on?
I'm here as well. I was just thinking about the question, trying to unmute myself.
So we do have a project that'll be looking at exascale systems. So systems with, heavy multi-core processors and then GPUs, and looking at how to build the stack we're building for Hive on top of that. So, that stack is primarily to support, analytics, particularly graph analytics. So it really will be our first work on trying to schedule threads, tasks, whatever you want to call them, and then move memory between the CPUs and the GPUs. So I think some of the stuff here would definitely be things we need to think about in terms of that scheduling and data marshaling.
Okay. And I was hoping, I didn't connect with Mike Lang to do this, but I know that some of those guys are interested, and Dave Beckinsale is also looking at some of this stuff. We're trying to work with his code for being able to, with Umpire and Chai, for being able to plug this in and try it out. So those are a couple other projects. Okay. And maybe you want to, George and Damien, among the things that we want to talk about here that we'd looked at, if when you essentially have resources that you use for managing the allocation and will eventually manage the data movement, that particularly if it's multidimensional, some marshaling and demarshaling may be involved. And so that's part of why we wanted to have a set for these resources. And there's an underlying mechanism in here where these can be decorated with, okay, there are different resources, but this is the one or subset that are supposed to be used for marshaling. These others for demarshaling. Here, potentially you can get down to the granularity of which copy engines you're supposed to use if there are several, and you really, really want to control it. Those kinds of things. So it's intended to be extensible into controlling those kinds of things as well. So what I know a long time ago you'd expressed some that a priority that we make sure that we handle multidimensional stuff. So does this look like it's headed in the right direction for the kind of support you're looking for?
So I think the basic functionality is here. The marshalling, right now we are doing it at our own layer because the multi-dimension thing, and because that's the engine that basically understands how the different memory layouts overlap. What's not clear to me is how we express this overlap at the bottom layer that you propose here. But if we keep the marshalling functionality above, I think that the interface you propose makes sense.
Yep, and there's no reason not to be able to keep that above, and that's
okay.
That's one of the things that I kind of find fascinating about Hi-Hat is that you do have a lot of flexibility as to, even for the same functionality of making trade-offs and choices about whether it's going to be implemented in something that gets plugged in from beneath, or you can manage all that, if it's complex and you want to make your own trade-offs as a client, you can do that all above.
So one thing that you didn't mention actually is about thread safety and the different type of limitation that you want to apply on these registration regions. One of the things, as an example, that we use pretty often to coordinate the different type of allocation is basically memory contexts that are shared between thread on a single socket, and they have limited amount of data that they can deliver. So it's like malloc, but specialized in a single context.
Mm-hmm.
How do you imagine that we can implement this on top of this interface, on the interface that you propose?
Yeah. So if you have a concern, let's see, in the general case, as I think is typical, multiple threads would essentially be contending for the same allocator. And so the implementation would then likely need to have a lock, right? It need to be thread safe, and it need to have a lock that says when you go to do allocations, I have to make sure that there isn't any other thread that's accessing it. That lock is going to incur inside the implementation, so it won't be visible to Hi-Hat per se. If you wish to avoid the cost of that lock and want to have a thread local nursery, such that you can do most of your allocation out of the thread local nursery and only occasionally go get a bigger chunk of memory from some common resource, you can also implement that inside your allocator. And you can register, you can have the same code, and so you can give the same pointer to each individual. You can sort of associate it with a particular execution device and with a particular logical thread on that device, so that it's really thread specific in that way. And as part of that, then you can have, and as part of the chooser, you can say, oh well, see, you can make the part of the choosing be used to select which implementation you're going to use, and you can also have additional information that's part of the execution policy blindly passed through to the implementation, so that the implementation can say, oh, when I made this call with thread ID 17, and I'll keep that distinct from thread ID 19's version, and we'll each get out of a different nursery. So you have that ability to pass that information through. Does that make sense?
So the kind of, let me try to see if I understand. So basically what you're saying is that
you're a little bit far from the mic. I can barely hear you.
Oh, sorry, I thought it. Sorry. Is that better now?
Yep.
Yeah, okay. So you mean that the thread safety is part of the policy? So when you select the memory allocator that you will use, you basically have to specify that I want to use it in a thread safe way or not. And then what you get back is a thread safe allocator or not?
I think I'd agree
Because
with the sentiment, but I would have used different words. And the words that it would, I think, open to doing something different. But I think that we essentially don't want to have Hi-Hat provide thread safety guarantees. But that Hi-Hat can give you the ability to choose from one allocator which is known to be thread safe and maybe slower, and another which is not thread safe but maybe faster.
You just said the word known, how it is known to be. That's something that I didn't understand.
Sure. I guess I like
because
saying that Hi-Hat's known.
Right?
So sorry?
I say it's a black box. You say that I can choose one of many, okay?
Yeah, but you as an agent, as let's say you happen to be wearing a Parsec hat. You as an agent are responsible for registering or knowing what is registered and knowing what the identifiers are for the choosers of all the allocators that you as an agent have registered. Hi-Hat doesn't register them for you, you do. Or you pick them from a known set of offerings that, Harry offered over here as part of his library. And so you can look at his, and he's got some that are over there, and you like his, but you like some other ones from Sally too. And so you're going to pick and choose between Harry's and Sally's. And your implementation operating above Hi-Hat knows what it is that has been requested or configured to be allocated. And so you know how to refer to those by name and what their capabilities are. And if you wish, we can take anything if we want to make those capabilities architectural enough that they want to be exposed as traits of allocators, we could do so. And if it makes sense to make thread safety one of the traits that gets architecturally exposed, fine, we can do that. But until you've made some particular trait or characteristic architecturally exposed, then essentially the agent which does the registering needs to have communication with the agent that uses what has been registered.
Okay, I think I get it. Thanks.
Does that design sound palatable?
Yes, but I was hoping maybe for a more dynamic behavior where other people can provide, I don't know, support for some type of memory allocation that I wasn't aware of dynamically, and then I would be able to extract this information at runtime and decide if I pick or not their allocator. Okay, so that's what I was looking for. If
you want to know, if you have some non-Hi-Hat way of looking up its capabilities, you can look that up. The only Hi-Hat way of looking up its capabilities would be to examine its traits, and the traits would need to be Hi-Hat would need to be augmented to understand and enumerate the relevant traits. So when you go to enumerate, when you query this right here, it says what the supported traits are.
Okay, makes sense.
So you can ask, is among the things that have been registered for this particular set of resources, are the traits that I'm looking for supported? And I can walk through those that have been registered and pick which one I want to use based on the traits. Or I can just walk through the ones and I can look at their identifier, like a unique number, and say, oh, I want to use 67. And I know what 67 is capable of. And you can do that dynamically, and that you can register stuff in the middle of execution too. You could say, oh, well, I was hoping to be able to do this during initialization or at the beginning of some phase. I can notice that I haven't yet registered, or no one has yet registered what it is that I want, so I'm going to go off and look up in some directory and find what's query some database and find what I want and cause that to get, you know, brought over and registered so that I can continue. You can do that if you want.
Yeah, makes sense.
All right. And I may just be ignorant. Is anybody aware of systems like this that have done this, particularly for allocation, that have sort of dealt with this kind of dynamic registration and being able to expose things as traits and so on? There may be some great work out there, but I'm just not familiar with anybody that's done quite this before. I'll take that as nobody's heard of such a thing. So if you do,
No.
Okay. All right. Any other feedback or questions or what ifs? Or yes, this looks useful, or no, I don't care. Okay. Good. So this is sort of, we're in the phase of wanting to try this out on existing systems and, you know, evaluate to make sure that it's functional, that it's effective, that it's performant, and so on. So as you have cases that want to work through those, we're interested. But if we don't have anything else, I think we're trying to queue up part 2 of our discussions on hierarchy for next month. Any other topics that people especially want to see covered? Okay. Well,
Thanks,
thank you
CJ.
very much, everybody. Wrap it up.
Yeah, thanks, everyone. So until next month, thanks a lot.
All right. Take care.